Recording. Okay, so we have lots to learn, and I'll tell you where we left off. We left off talking about Newton, and it got to be like 1680. And here's the deal: you can close computers. So anyway, Newton has done some decently famous, good stuff by this point, but it's not what he's really famous for. That's coming up right now. There was this outstanding question that I've tried to raise. I've tried to motivate the question. Why the heck Kepler's laws? Like, what makes them true? Why would this be? Kepler figured it was something the sun was doing, but he was wrong about how and why and, things like that. He had that wrong. So anyway, people were thinking about that. It was an outstanding problem. And as I think I was hitting to you before, I think I said this, science was becoming social a little bit. Scientists were starting to talk to each other. There was this little outfit in London called the Royal Society of London. It was a group of people who kind of got together and chit-chatted about stuff now some of them were professors. Newton was. He was a member. Kind of unusual for him to be a member of anything, but he was. Some of them were like aristocrats who had money and servants, and they had time to tinker with new stuff in their basement and then discuss it at meetings. So there was this Royal Society meeting one night. I don't know if Newton was there, but if he was, he went home early, because he always did. And these people, Robert Hooke, and by the way, while you can't find a list of his sins online, you can find his entire diary.
Oh, that's rough.
Which is kind of gross.
I hate that.
He had a tendency to put lots of things in his body, see what happened. Usually it was bad, which he tried to fix by putting other things in his body.
So please tell me he put the things in his body through his mouth.
Yeah, mostly. Yeah.
Okay. Mostly.
No, he did. Anyway, Robert Hooke did important stuff. He was a pioneer in microscopes and springs, and he's a good scientist. Anyway, there was another guy, Christopher Wren, and these people, it's not like I'm going to quiz you on these people exactly. I just want to let you know he's like this guy who designed London after the big fire, and he's a big deal. And then there was this guy here who you might have heard of, at least his last name, Edmund Halley, something like that.
Comet?
What's that?
Halley's Comet?
The comet.
Yeah.
This is the guy who predicted a comet coming back. It got named after him for him predicting it would return. Because people didn't know before that comets were things that returned. That was the new idea. And it has to do with Newton. Anyway, they're sitting around, and I used to tell the story incorrectly. I'd read the history of this, and I used to tell it wrong. I used to say they'd gone down to the pub. I visioned where would they go after the meeting. They went to some social place. It wasn't the pub, it turns out. I learned a few years ago. That's not what they served there. It was a
coffee house?
Yes.
Oh yeah, because this is during the Enlightenment, right? In the coffee house.
They went crazy with coffee. Right? Instead of going and getting inebriated and talking about God knows what, they started getting hyped up on coffee. Coffee was a thing. It was actually a significant societal thing for people to stay up late at night talking about stimulating stuff while stimulated. And that's what they were doing. They were at the coffee house, and they had a bet going. And basically, Halley said, hey, whoever can tell why Kepler's laws are true wins. Wins like this fish book that they published and cost too much money, and they had spare copies of. Anyway, it was a stupid, called The History of Fish.
Ooh,
Had all carp and bass.
Is that actually what it was?
Yes, really. I'm not even making that up. So they had this bet going, and the bet was, who can figure out what makes Kepler's, I'm paraphrasing, but who can figure out what makes Kepler's laws true? Hooke said, I know, inverse square law, central force. And then Halley says, how do you know? He said, I'm not telling anybody.
Oh, got him.
Why not? It's so hard, and I'm the only person who can do it. I'm going to wait till everybody else suffers while trying to figure it out, and they realize they can't. And then when I show my proof finally one day, you'll see I'm the greatest. Gee, well, you know what?
Dang, so.
He never told anybody his proof, because fact is he probably didn't have one. He probably had a hunch, a good hunch. Turned out he's right, but he couldn't prove it. Anyway, so next time Halley's talking to Newton, by letter, I think, Newton says, I know that. What? Inverse square law of central force. And I'll explain what that means in a minute. I'm going to get to that. That's what Robert said. By the way, Robert Hooke and Newton were enemies, frankly. They kind of respected each other, but still.
They were rivals?
They were rivals, almost enemies. A little bit nasty with each other. One of them had undermined the other one somehow, and it had done them dirty. But anyway, so Newton told Halley he had the proof. And Halley took a risk and unannounced went to Newton's house, showed up. Fortunately, it went well. Halley was a good people person. Halley knew how to butter people up, make them feel good about themselves. That's a good skill in life. And Newton is not one to like accept visitors generally, but Halley shows up, he lets him in, says he's got the proof, says he can't find it right now, says get back to me pretty soon. Halley's like, dang it, he's probably just like Robert Hooke. But no, Newton sends him this manuscript of like the proof of it. Now what I want to do, I want to try to convey to you what it was that we're talking about, and then put the gravity thing together. I am choosing right now, yes, I'll do it. I'm going to do a very quick mathematical proof. You do not have to know it or reproduce it, but please watch, please try to follow. It's a little tidbit of what Newton did. So, you should have learned in physics about this thing called centripetal force that's like that.
Yes.
F sub c is mv squared over r. It's like something with a mass of m going around in a circle, radius r, at a speed v. That's how hard you have to pull inward on it. Newton knows this, because Newton is Newton, and he's figured this stuff out. Then Newton says, I wonder why the law of periods is true. Let's just take that one, the law of periods. Why? Why the law of periods? He does a substitution. Speed when you go in a circle is how far around the circle is divided by how long it takes to go around the circle, because speed means distance over time.
Yes.
So you substitute this in like this, and then that gives you, I've done this lots of times, let's see, 4 pi squared r squared over t squared over r, and then you can come down here, and that's 4 pi squared r m over, but that's r squared, over r t squared, but one of the r's cancels out, and then it goes t squared, why that's supposed to be r average cubed.
Yeah, Jace.
Remember Kepler's law of periods? T squared r average cubed. So he says, okay, so it's a constant times r cubed. I'm simplifying this and considering only circular orbits in this thing. So you get this. And out goes one of the r's, leaving a square. You can put the little 4 pi squared, and there's an m in there, sorry I forgot my m. You can put this aside and say 1 over r squared, say this is all just some constant. Therefore, that's what that means. The centripetal force is proportional to 1 over r squared. Now what does that even mean? Let's talk for a minute about what that means. That means that this force that the sun is doing gets weaker with distance. It fades away.
That explains the speed thing.
Well, it's going to. So it fades away with distance, in a very particular way where if you made a graph of the force, this force, it would be in a steep dive like that.
Okay.
For those of you who took EP physics, especially for me, anybody took EP physics. Remember the power laws?
Yes.
It's a -2 power law. It's the real steep curve. It's the kind of thing where when you double one thing, you cut the other one, ouch, down to a fourth.
Wait, I don't remember this at all.
I don't remember this at all either.
You know?
I had Dr. Clark. I don't know if he taught this.
He probably should have some. Anyway,
There was also-
I make a big deal of it, and it's like this. You tend to think in terms of inverse proportions. Like most people think, like if you got like twice as far from something that was getting weaker, it might be half as much. No, a fourth. What if you get 3 times as far from something? 1/9. Get it? What if you're 5 times as far away?
1/25.
What you got it. You got the pattern, right? So Newton says the sun is doing something to the planets that mathematically acts like this. Honestly, Hooke had the hunch, but Hooke couldn't prove it, or he never made good on it. They called his bluff. Frankly, they called his bluff. He never told anybody how he did, because he didn't. But anyway, Newton called his bluff, produced the proof. It goes beyond this. It's more than just this. In the involved math that Newton did, he also showed that this would necessarily produce elliptical orbits with the sun at one focus. He explained it mathematically with that. And there's one other law, the law of areas. Now this one, I like talking about this. Yes?
Can you explain what R is again?
R is the distance from the object that's pulling on you.
So
The reason for using R is because originally, what distance were we talking about?
Radius.
The distance from the sun, the radius of an orbit. So the context is this. You've got the sun here, you got a planet going around the sun, and that's the radius of its orbit around the sun. I know it varies, I know it can vary, but that's also the distance from the sun. Jordan?
The sun, so, right, because the sun is one photon.
Yes.
So it's going to vary, so R is really R average.
Well, what I did here, to keep it simple, because I just wanted to give you a taste. Besides, I don't think I can do it. Like it's Newton, he's smart, you know. But this is the simplified version where I consider only a circular orbit.
Okay.
So then R is the only R you got, and it's the distance. Now, there are a lot of things in the world that act like this, that do inverse square laws. Here's an example. Completely unique example. I don't know if anyone else in the world uses this example. Imagine somebody comes running down the hall and throws something in the room, and you go, oh no, it's a grenade. And it's like, this is awful, right? That's a horrible example I'm giving, right? And one of you tries to be altruistic and jump on it, and it goes off, and your life flashes before you, and then you're still here. Everybody's okay. Stings a little. There's little things all over you. They're gummy bears. Oh, it was a gummy bear grenade. It was just this thing that goes off and splats gummy bears on everybody. See, I'm not getting anybody hurt in my examples. So you got gummy bears. Guess who got the most gummy bears? You did. That's what you get for being all altruistic and stuff, right? So, so whoever's closer catches more of them. What if you wanted to catch gummy bears with like one of these? If you were close to it, the radiating going out in every direction in three-dimensional space, gummy bears would be more concentrated closer in, right? So if you were like, say, 3 feet away and caught them here, maybe you get like 100 gummy bears.
So go jump on grenades.
Well, no,
Where can
what
I
if?
get these gummy bear grenades?
Where did I get the idea?
No, where can I get them?
Oh, where can you get them? I don't know. Maybe you can be the first to market them. Give
So
me a
if
cut
you
of
go to a
it.
store and buy like a normal.
All right, listen. Shh. Listen. What if you were twice as far away? Do you see that in the vertical dimension here, half the gummy bears are not going to miss you? And the same argument can be made in this dimension. So they're only going to get half of a half. In fact, it would take what? 1, 2, 3, 4 of these things to catch all the same gummy bears. Do you see that any influence that radiates outward in three-dimensional space is going to decrease like that? You're covering a larger area the further away you get. It's not that the thing gets weaker or tired or something like that. It's that it spreads out and is shared among more area. So it's not an unusual kind of thing. Light works that way. The intensity of light. If you have a light bulb in the middle of the room, the further you get from the light, the dimmer the light gets. Not because the light got tired. Not because the light bulb actually gets dimmer. But because you're just catching a smaller share. Do you get it?
Yeah.
That's the kind of thing an inverse square law is. Yes, Emma?
Wait, so if there are 3 dimensions, why wouldn't it be half, half, and another half?
I get you. It spreads out in such a way that it's over an area,
Not a volume.
not a volume. But the thing is, if we lived in a 4-dimensional universe,
There would be.
it would be an inverse cube law.
So if we lived
Isn't
in
that
a
neat?
5-dimensional.
Then it'd be an inverse fourth law. And you know what? I played with the program and you saw power of R. That's tied in with the dimensionality of space. I mean, this is deep. But anyway, Newton figures that out. He figures that it also makes the orbits ellipses with the sun at one focus. And there's one more thing that's actually simpler. I'm going to refer to something. Let's see if these names mean anything to anybody. I used the same example in physics last year, so I bet some of you know. Who is Tanya Harding?
Oh,
Who's Tanya Harding?
isn't she a tennis player?
No, what do you know, Maddie?
Skater.
She's a figure skater.
She was.
Turned
Turned
wrestler,
yeah,
boxer,
wrestler.
stuff like that. That's a strange career transition. What necessitated her career transition?
Well, she accidentally hit this girl's leg before a competition.
She was going to be like a potential gold medalist in the 1994 Winter Olympics. And so was maybe Nancy Kerrigan, her rival, kind of like Newton and Howell, her rival Nancy Kerrigan. Only right before the Olympics, somebody hired by a guy named Jeff Gillooly, who was Tanya Harding's boyfriend at the time, comes in the room there where Nancy Kerrigan is right before the Olympics and whacks her in the knee with a great big stick. Almost broke her kneecap. I mean, really, really injured her bad, and ran away. He was hired by Tanya Harding's boyfriend. Tanya didn't have nothing to do with it, right? There's a whole movie about it. I haven't seen the movie, but there's a movie about it.
There's also a Sufjan Stevens song about it.
Really?
Yeah.
Well, how about that? This is cultural, famous stuff. Anyway, what does this have to do with anything? Okay, the news, back before they had pandemics to talk about and stuff, back in 1994, the nightly news, every night, I know, I was there, it'd start with video of Tanya Harding and Nancy Kerrigan figure skating and spinning like some whirling dervish, looked like if you put a propeller on their head, they'd take off. I mean, how do ice skaters get spinning so fast?
Don't they hold?
What do they do?
Isn't it yeah, they.
I can show you.
You hold your arms out and then
I'm going to show you. Now, I'm not going to show you by figure skating because I would fall flat on whatever if I even tried. But, okay.
Is it kind of like how you do multiple pirouettes in ballet?
Oh, I'm sure it's like that. Oh, it's like this. Here we go. I'm going to do it. Sorry you can't see on the recording. I'm going to have a bunch of mass, way out here, and I'm going to be going kind of slow, and then I go, look, I can do just what Tanya Harding did. Except I did. Did you see me go faster when I did that?
Yeah.
Okay, you put that there. Okay. Anyway, why did I go faster? It is a physics thing. It's called conservation of angular momentum. It's a thing. I'm not going to go into it right now. There's this, a little bit, but there's this product of mass, radius, speed, and the sine of an angle. And all I'm going to say about that is, this quantity is conserved, neither created nor destroyed, if there is no external torque. torque is twisty force. Torque is what you do with a wrench when you try to tighten a bolt.
Is that the scientific name, twisty force?
That's mine. Okay, so torque is when you try to like do a force with a length of a wrench, you know, and you push like that, and you can exert the same torque with a long wrench, not pushing very hard because you get more leverage, right?
Okay.
You know, that whole thing. So the only way your angular momentum is going to change is if you put a torque on something. The thing is, if the angular momentum doesn't change and the radius gets smaller, the speed must compensate by getting bigger to make up for it, to keep this constant, right? So what this says is the sun does not do twisty forces on the planets. The sun does not do like that, like Kepler erroneously thought. What could the sun do to exert a force without doing that? It could do, you know, this. The very fact, now listen to Kepler's law of areas. Do you remember how with Kepler's law of areas, the V at perihelion times the perihelion distance was equal to the V at aphelion times the aphelion distance? You see, that's a product like this, isn't it? Newton realizes that what's going on is planets are conserving their angular momentum because what the sun is doing to them is not this, but this. It's pulling in. So listen to the logic is how we're about to put this all together. Newton has now figured out that the sun is mysteriously pulling on the planets, unless you want to be a super conspiracy theorist and think that some weird thing out there is pushing things toward the sun. Take your pick. Probably the sun doing it. So anyway, the sun is pulling on things with a force that acts like this. Now, if he had stopped there, that would have been a major accomplishment. We would now have the golden rule for Kepler's laws, the thing that unites Kepler's laws. All it is, it's just this. This is it. You don't need all of Kepler's laws. You just need that, and you've explained the motion of the planets. But wait, there's more. It gets a lot better. Because Newton also stops and thinks, wait a minute. Jupiter's moons go around Jupiter. It's seen with a little telescope himself. Jupiter's moons go around Jupiter, and you know what? You can't quite see it from the side, but they do go in elliptical orbits. You can check the periods of them. That's easy. You watch them. They obey Kepler's laws going around Jupiter. Why? Because Jupiter pulls on them with a force like this. Oh, wow. This mysterious thing the sun does, Jupiter does it too. And Saturn does it to its moons because they're doing that too. Wow.
It does it to our moon, right?
Ooh, what's the next step. So our moon goes around us in an elliptical orbit with the Earth base. Well, there's a little bit of wobbly thing going on I'll leave out. But with the Earth at one focus, it obeys Kepler's laws. Actually, here's a little quibble. This is a trick question. Your job is to figure out how it's a trick. Does the moon, our moon, obey the law of periods?
Yes.
Yeah.
You say sure, yeah. It's a trick question.
Is that Newton's third law? How it like
Well,
has the same force that
no, that's not the trick. Here's the trick. Listen again. Listen closely to my pronunciation and grammar. Does the moon obey the law of periods?
No, because it's only one.
Yeah. You can't say. You see, if you made a graph of all the planets' periods and radii like this, you get a bunch of dots and makes a curve. Great. You want to make a graph of the moon?
You get one dot.
Yeah, it's a moot point. You can't really say. However, you know what? We now have lots of satellites, and guess what? They're at different distances, and they have periods, and guess what? They all obey the law of periods. Yeah.
I thought the law of periods says that it's repeating.
No. You're thinking of one of Kepler's starting assumptions that planets actually have periods. That's not the law that tells how the period's related to the radius. That's just to say that I think they have periods. Meaning they do the same thing over and over again. Kepler's law of periods is much more specific than that. It's that the squares of the periods are proportional to the cubes of their average distances from the sun as a group.
So you can't measure just one movement?
Well, I mean, you measure its period, you can measure its radius. It's just like, what shape is that graph? I don't know, it's just one dot. I can't say what shape it
What
is.
was the graph that you used for the
Oh, that's like lots of planets all going around the sun. If I got lots of data points, I can get a curve. All I was saying is, and I don't want to make too big a deal of this, but I'll try to clarify. I was simply saying the law of periods is not about a planet. It's about a group of planets.
Okay.
And how they're related to each other. As opposed to the law of elliptical orbits, which says that each planet has an elliptical orbit with the sun at its focus.
Right.
And each planet line from it to the sun sweeps out equal periods and areas in equal times. Law of periods is a collective type law. Yeah?
At this point in time, did they know exactly how the planets were like set up and like how it was heliocentric? And
Yeah, it's a good question. It's rapidly becoming kind of standard. Newton had no doubt about it. Newton was sure, but you know how ideas spread through academia and stuff?
That's what I meant.
It's like the core scientists who actually did this stuff, all of these people by 1680 believed the planets went around the sun. There were still people debating it, but they weren't mainly the main people working in the area. So yeah, the idea is pretty much spread. And it's going to spread ever so much more as soon as Newton does this. So, but wait, there's more. So Newton suspects that the Earth is pulling on the moon. Okay? So that the moon's accelerating towards the Earth, following, it can't get down. But then he remembers being on the farm during the plague at Woolsthorpe and watching, yeah, this is the thing, apples fall. And apples accelerate toward the center of the Earth. And you might think like, well, yeah, you know, of course they do. Like, did you ever think like,
Back to Earth.
yeah, listen, did you ever think like, what's the big deal about Newton? Like he's some guy who like saw an apple fall, thought gravity, and like that was supposed to be impressive or something.
Well,
I mean,
the first thing that I learned about Newton was probably like the laws and stuff, and I was like, well, he's wrong because I didn't know what friction was.
oh,
Like,
yeah. I mean,
how does that work?
It disagrees with Aristotle, who people tend to think like if they don't
Yeah.
learn Newton,
So that was
because of the ubiquitousness of friction.
And then I went to like a museum. They showed how it worked.
And then it made
How
sense.
worked.
Click.
Yeah.
Now, here's the click that happens with Newton. He suddenly realizes the commonality, the similarity between what an apple is doing and what the moon is doing. They're both accelerating towards the Earth, and he is one step away from a grand idea. And I'll tell you the step in just a second. Yes?
Okay, it might be sort of off topic, but it has to do with gravity.
Okay.
Okay, so like, really small, like, particles and stuff like that, do they follow the law too, because they have mass also?
Yeah, they do. It's just that little particles like, say, electrons or something,
Like are
they're
they-
supposedly subject to gravity. I'm sure they are. But they are subject to electrical forces which are vastly, vastly stronger on them. And so you don't worry about, oops, I dropped an electron. You know, it's like, where's my electron on the floor somewhere? You know, it's orbiting an atom because it cares a whole lot more about that than it does about the Earth pulling on it. Yes?
So is that why like the strong force and the weak force are like stronger than gravity?
Oh, well, we're going to get to them later. Later on, toward the end of the semester. Anyway, assuming I can get anything done. Okay, so let me get back on my. No, that's great. No problem. So Newton thinks, is it the same thing? Could apples be influenced by cosmic forces that control the heavens? That'd be weird. That'd be like the heavens and the earth are all part of the same thing. It's going to be called the universe. So in a way, he's about to discover the universe in the sense of a universal law governing everything. So,
Did the word universe?
I don't know. It's a good question. I should check. Good question. So anyway, here's what he does. He says, if I'm right, Well, I'll ask you. Do you think that, okay, hey, what's the acceleration of an apple?
10 meters.
You know, 9.8, about 10 meters per second, you know, toward the earth. Great. What do you think Newton had a hunch the moon's acceleration would be?
9.8 meters per second squared.
I just led you into that trap.
No, it's further away.
He didn't, right. He did not think it would be 9.8. He thought it would be, Jace, more or less? Less. And the question is, oh, how much less? And here is his answer. And Jace, I think you're onto this, so I'm going to let you see if you can tell me. So here's what he figures. He sort of like invents/discovers calculus to show that the right place to measure from for this force is the center of the earth. So this is a distance r of the earth, r sub e. And there's an apple, r sub e plus, I don't know, 20 feet. You know, who cares about the 20 feet? It's the earth, you know. The moon was way out yonder. They knew how far away the moon was. Even Ptolemy knew how far away the moon was pretty accurately with parallax. Amazing. 60 Earth radii. Jace, I think you're onto something here. I think we're going to find out. What do you think Newton thought, as a hunch, the moon's acceleration ought to be? You're on the right track. Can you get there?
Is it 60 squared? Like, inverse?
9.8 divided by 60.
That. See what he's thinking? He's thinking it's that candy hand grenade thing where influences get weaker as you go, and he's already figured out the sun's doing this to the planets, Jupiter's doing it to its moon, Saturn's doing it to its moon. He thinks maybe the Earth's doing it to our moon and even apples. And so it turns out this number is 0.00272 meters per second. And he checks because he can do this. He knows the speed of the moon. He knows the radius of the moon's orbit. He plugs in the things. He calculates it. And it turns out the moon's acceleration is just what he thought it might be.
So it's constantly getting faster.
No, it's just bending around towards Earth. It's a centripetal acceleration, meaning it's changing direction, not really changing speed particularly. Yes?
In terms of like the equation 1 over, we said there was 1 over r squared, so how did he replace the 1 with 9.8?
It's a proportionality, meaning I'm comparing two things. So like, how would the acceleration be different if I change this one factor, like how far it is? And if something is proportional to 1 over the square of something, that means whatever you do to the distance, you do 1 over the square of that to the, like for instance, if you were 10 times as far away, 1 over 10 squared is 100th. The acceleration would be 100th of whatever it is in the first place. Yeah, you're just comparing things. Now, look, I want to point out, this is a hunch. This is a real world calculation. And his hunch was right. So he goes, that's it. I've just found out that the Earth does the same thing to apples and the moon that the sun does to the planets, that Jupiter does to its moons, to Saturn does to its moons. Oh my gosh, it's like everybody's doing it. It's like a fad or something, you know. It went viral. This thing where you pull on stuff with an inverse square law of central force. And what gives you the right to do that? Maddie?
Why didn't he just use the acceleration equation in the first place?
No, okay, I think what you missed here is the difference between what's going on. This is a hunch based on the clever suspicion that the Earth is doing things to the moon and apples that the sun does to the planets, and that it ought to be this inverse square law thing. He doesn't know that it is. It's a hunch. This is where he actually takes the moon's actual speed, actual distance, plugs it in, and proves that his hunch is correct. See that? So now the question is, we're almost there. The question is, what gives things the right to go around pulling on other things? Like what is it the sun has that gives it the right to pull on planets? And apparently the Earth's got it too. But you know that third law, forces come in pairs, equal and opposite reactions? It takes two to tango. It ain't just their fault, it's their fault too. So in other words, when the Earth pulls on an apple, it's not just that the Earth's pulling on the apple. The apple's pulling on the Earth. So the apple's got the power too.
Well, it's
Small
very
power.
small power. but
Well, the thing is, the force between the apple and the Earth is the same in both directions. The apple's pulling absolutely every bit as hard on the Earth as the Earth is on the apple. But Newton also knows, and so do you, that two different objects of different masses, watch, fall the same. You see that? That can only be true if, see, this is harder to accelerate. I can tell. This is easy. See? You can tell by my voice, right?
Yeah. Yes.
See, that's the voice that tells you. So that can only be true. Like if this thing is 10 times as hard to accelerate as this, and yet they accelerate the same, this is being pulled on 10 times harder, which means apparently your ticket to play this game is your mass. So apparently mass is what bestows upon you the power to go around pulling on things. And you're doing it right now according to this. I mean, if I took any two of you, whether you like each other or not, you all like each other, right? Oh yeah? How much? This is how much. This is how much you each like each other. It's called Newton's law of universal gravitation. Newton is now proposing something that maybe you already knew. Maybe you've heard it for a long time. Maybe you just accepted it because, yeah, that's what you learned in school or something. Newton is claiming, and some of you, maybe it didn't quite cross your mind that this is the real thing. Newton is saying that every physical object in the universe pulls on every other physical object in the universe with a force whose strength is described like this. You see, it's proportional to each of the masses. The more mass you got, the more pulling you can do. You got the power more. The more mass the thing you're pulling on has, the more it's got to, it's like this. There's more to love with, and there's more to love. And okay, and so like for example, if you've got 1 kilogram and 1 kilogram, this kilogram only has 1 kilogram to love and only 1 kilogram to love with, right? Mm-hmm. But what if this was 2 kilograms and 3 kilograms? Each one of these 2 kilograms loves all 3 of the other.
That's a lot of kilograms.
That's six loves, right? 6 times the love, isn't it?
Mm-hmm. Yes, sir.
Get how that works? So you multiply them? Okay, so this is Newton's law of universal gravitation. I'll very quickly point out that the value of big G, I talk more about this in AP physics, I don't have time right now. The value of big G, it's a constant. Newton was not able to figure it out, as smart as he was. The reason he couldn't figure it out is because the force is so pathetically weak that if he took 2 laboratory masses, these kind of things, and put them some laboratory distance apart, he couldn't tell they were pulling on each other. He had no way to measure the puny little force between them. Yeah. He couldn't measure the tiny, tiny force. And when the force is big enough, like this force here, I'll measure force. Ha, Newton, in your face, Newton. Watch this. I'll measure force between 2 masses. Look, I'm measuring one right now. I'm just measuring this kilogram is loved by the Earth with 9.8 newtons. So why don't I just plug those things in? I'd have to plug in the kilogram and the radius of the Earth. I know that. The force, here it is, and the mass of the Earth. Oops, don't know that one.
Uh-oh.
You see, you're stuck, rock in a hard place?
Yes.
Big rock in a hard place. Anyway, sorry. Yeah, okay, yes.
You know how you, like, to find the acceleration of movement, you divided, like, the gravitational constant here?
By the ratio of the distances squared. Mhm.
So does that mean G M1, M2 is some type of acceleration because you're dividing it by M squared?
Well, you get an acceleration if you divide this by one of the masses. Then you have a force over a mass makes an acceleration.
So,
Every day.
I'm trying to figure out how you can, oh, you're getting to the dimension.
Okay, all right, listen. Newton never figured it out. About 50 years later, a guy named Henry Cavendish did a brilliant experiment that I would think would be motivated by having a baby. He didn't have a baby. I don't know, maybe his wife did. But anyway, if you hang a thing by a string, it can be da 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 over the crib, you know, the little mobile thing.
Yeah.
You ever notice how incredibly easily they turn?
Yes.
God, you could probably breathe on it through a mask. I get it to turn.
Yeah.
So Cavendish thought of using one of these as an incredibly sensitive force measuring device. He hung a stick from a string, put a big mass here, a big mass here, separately mounted another mass here, so that this mass and this mass are attracted trying to twist it. It put a twisty force on it. It twists the teeniest little bit. You could hardly even see the twist. He had to put a mirror on it and bounce a light all the way across the room and look on the wall at where the light showed up on the wall, at the reflection, and see it move like an inch across the wall because of a tiny, tiny turn. You see how incredibly tiny the force is between ordinary masses?
But he proved it.
But he found it, and the constant is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared.
That's so cool.
It's such a pathetically small thing that you probably don't even, you go through life not realizing you're attracted to everyone you meet. You didn't notice?
Mr. Ahrensberg?
Yes.
Two things. One, I'm attracted to you, and second, isn't that Avogadro's
You couldn't help
number?
it.
Isn't that
Neither.
Avogadro's number or something?
No, it's not Avogadro's number. This is the universal constant of gravitation. And by the way, I can tell you how much you're attracted to each other. The person sitting a few feet away from you, safe distance away from you, whoever it is, if I took the two of you way out in space somewhere, way out there, out yonder, and put you out in space and left you alone. Yeah.
He died.
No, well, you're in a spacesuit. You're in a spacesuit.
We die together.
Yes. What would happen, I'm not kidding you, is the two of you would approach each other very gradually and meet in, I've recalculated this in a while. It's roughly like a few days. The acceleration you'd have towards each other would be at first completely unnoticeable, but after a day or so, you might go like, get fresh with me, you know, like. Do people still say that? No. They don't say that anymore. Nobody. People said that. People said that. Showing my age.
God.
Hey, did you at least know the phrase?
Yeah.
You didn't.
No.
Oh, you. I'm so old. Yes.
So how far apart would they be initially?
Let's say like 6 feet apart.
Wow.
Like that. And then within a few days, you're together. At last. Okay. Now, another thing you could do. Listen, instead of, like, let's just say that Gavin doesn't want anybody getting fresh with him. So he takes fresh fruits and vegetables and holds the fresh fruits and vegetables at different distances from him and gives them tiny, tiny little barely palpable taps.
Stay away from
And puts them in orbit around him. And so Gavin is being orbited by star fruits and broccoli and rutabagas and all kinds of things.
Star fruits.
Yes. Okay. And you know what those things are doing? A line drawn from the star fruit to Gavin shall sweep out equal areas in equal times. They will orbit with elliptical orbits with Gavin as one of the foci. And as a group, the squares of their periods shall from this day forward be proportional to the cubes of their average distances from Gavin. Because Gavin has just as much right to have a solar system as the sun does.
The god of flame.
Yes.
Go for it,
How
guys.
Jordan.
long would it take an ant can use
How do you know I
to
don't?
get, like,
I'm not. That wouldn't be a whole lot different numbers. You could. I'm not going to get into calculations right now, but I'm saying this is a big idea, isn't it? Let me tell you how big this idea is. Yeah.
What would happen if you had like something orbiting in an elliptical pattern and you had two massive objects at each foci?
Oh, the orbit would be more complicated, and the two massive objects would try to pull on each other too, and it'd be a mess. It basically would be the three-body problem. That unsolvable thing that the professor set up wrong. You know. So listen, this is a huge idea that Newton has come up with. It's the idea that the entire universe and everything in it are bound together, or at least attempted to be bound together, by a cosmic universal force. Newton could not explain how anything did this. That's quite a challenge even today. Einstein has another way of looking at it involving the curvature of space and time. You know, that's something I'll mention in a little while maybe. But anyway, so he's come up with the universal law of gravitation. By the way, Halley became his agent, meaning Newton was this depressed, middle-aged guy, subject to bouts of melancholy and so forth. I'm going to wildly speculate he could have been bipolar, because he would have periods of like real depression, and then if you got him going, he went nuts and like stayed up all night and wouldn't eat and like worked like crazy.
Depressive thing or like anxiety that's like really, really bad.
Who knows? I don't know what all his problems were. I mean, after all, he did want to burn the house down with his parents in it. But in any case, I want like diagnosing retroactively. That's kind of a strange habit. But I'm just saying, Halley said, "You've got to tell the world, and I'll be your agent." Halley stayed on him. Do it, Newton. Do it. Like, write your book. And Newton wrote this phenomenal book called Principia, which changed the world. It may be one of the most, no, I'm not going to say maybe. It's definitely one of the most important books in the history of humanity, because it ignited the entire, like the Industrial Revolution, for better or worse, whatever. It changed this world. And it gave us a concept of the universe, that all these things are all pulling each other. Now, I got some other ideas I got to talk about. I'll tell you what, I won't take up the homework Monday. I'm almost there. But we actually have to apply this law some. I will see you Monday, right?
Yes.
So we're going to try to wrap this stuff up on Monday. Yes?
I wanted to ask, what's the difference between the Principia and the Principia Mathematica?
I think it's the same book.
Okay.
Yeah, it's the same thing. It's Principia for short. It has all Newton's laws in it. It's a brilliant masterwork, and it got people rolling. It's not that people didn't do a lot more sense. They sure as heck did. But it stood out as like such a seminal seed-bearing, thing that you got to make a big deal of it. I have to. Anyway, this is the idea that we care about. And so what we've got now, suddenly all kinds of things are falling into place. Like planets. Like, guess why we have planets? Because a bunch of little bits of stuff all loved each other and got together. Guess why we have stars?
Also the same reason.
Because a bunch of gas all loved each other and got together in a big pile and squeezed together so hard they get so hot they start nuclear reactions in the core. The universe, that idea that, and Newton was keen on the idea that there ought to be universal laws, because he was also really, really into theology, and he thought there was a God who made laws and figured, I'm going to find them. Whether or not that's the case is a whole different thing. But that's one reason he was into this. He was seriously into theology, biblical chronology.
He
and stuff.
believed in God, but God created physics
Yes.
for him to figure out.
Yeah, that's what he thought. You got it.
So he didn't believe in like
Well,
creation.
Hey, wait, let's listen. Let's listen.
Throughout the day, go to Tomorrow's office in the lounge. T-shirt for $10 and wear the pattern uniform next Wednesday. Please have your WA live show up and running. Begin after the bell.
Newton was kind of a nasty guy.
Okay, I'm going to start this. Let's see. By the way, I feel like we got the big idea across. What we need to do now is apply it some. You should now be able to answer, for your homework, you should now be in a position to answer just about any non-numerical question. Like we told the story, the history, and how these laws worked out. That I've said. There's also that Newton and gravity handout. I mean, like PDF I gave you. So let's watch WA Live.
Wait, Ms. Sandberg, so it's not due Monday?
It's no, I'm not going to take it up Monday, probably Tuesday or whatever the next day is.
Sure.
But get close, get close.
Random question, do you teach any freshmen?
I don't have to teach any freshmen.
Alright.
There we go. Everybody quiet so we hear the announcements.
See your winner email for more info and a link to attend. Second and fourth application parties for seniors is next Wednesday. Drop them during lunch and community time.